Good morning or afternoon, wherever you may be. My name is John Nolan, and I will wrap up this tutorial by telling you about fluorescence-based EV size measurements, which we perform using vesicle flow cytometry. First, I'm at the Scintillon Institute in San Diego, where my group develops new technologies for cell and molecular analysis. We do most of our biology through collaboration with academic and industry groups. I'm also the founder of Solarcus Biosciences, which offers some of the tools I'm going to describe today as services and assay kits. What I'm going to tell you about today is I'm going to give you a little bit of background. I'm going to emphasize the role of instruments and assays in vesicle analysis, and I'll highlight again the guidelines that have been recently produced for reporting EV flow cytometry methods and results. Then I'll describe the vesicle flow cytometry or VFC assay. I'll talk about characterizing the instrument in order to validate it for VFC. I'll describe our vesicle size standard, and then I'll describe and demonstrate how we use that to calibrate the surface area of EVs, which is how we estimate size. And then I'll wrap up by comparing and contrasting the different approaches to EV counting and sizing, and talk a little bit about how the integrated use of these methods enables rigorous and reproducible EV measurements. So first, when people ask me about how to measure vesicles, most often they focus on the instrument, which might be distinguished by its, lasers or detectors or collection optics that might make it more or less suitable for measuring EVs. But often what people fail to recognize is that the instrument is only a small part of the overall assay. And the results of an EV analysis will depend heavily on issues like sample staining, any wash steps, how you decide to use your flow cytometer in terms of a trigger channel or fluidics, and then obviously calibration, gating, and reporting all have a major impact on the results that are reported. And it's that realization that led to the development of this guidelines framework, where all of those aspects that contribute to the measurement of EVs, including the instrument, but also all of the other parts of the assay that are so important. So that little bit of background, let me describe for you our vesicle flow cytometry assay. It is a fluorescence-based assay that employs a fluorogenic membrane probe to selectively stain membrane particles, and together with properly validated fluorescent antibodies, enable the selective detection and immunophenotyping of individual vesicles. Calibration of both vesicle size and immunofluorescence are key to that, and I'll get to those next. In its commercial form, the vesicle flow cytometry assay contains a detailed protocol for assays, which are all performed in 96 well plates. This is to encourage reproducibility. Likewise, the data analysis is very standardized. It takes place in FCS Express, which is a nice general purpose flow cytometry analysis software, and has the nice features also of being able to do parameter math, which is important for calibration. And it's also available in a reader format, which many people find useful if they don't have the full version of the program. So appropriate calibrators and standards are an important part of any assay. And in the VFC assay, we use several. We use a synthetic lipid vesicle that I'll describe in a little more detail as a vesicle size standard. It also serves as the negative control for immunofluorescence. We have bead-based fluorescence intensity standards and antibody binding standards that are useful for rigorous and reproducible fluorescence measurements. And then we use actual cell-derived EVs as appropriate, especially for immunofluorescence. So first, let's just say a couple words about instrument characterization, because all of assay performance will depend on a properly characterized and optimized instrument. And here, as for conventional flow cytometry, multicolor, multi-peak rainbow type beads are very useful. Your commonly available 8-peak rainbow beads will work. We've developed a set of 4 nano rainbow beads that are a little better tuned to the brightness range we'll encounter in EV analysis. And we use these beads to characterize several aspects of the instrument. We use the CV of the bright bead to report on laser alignment to make sure our lasers are well aligned across all lasers. The bright bead is also calibrated in terms of its concentration, so it serves as a counting bead for purposes of calibrating your sample flow rates. The performance on the individual fluorescence channels is evaluated by a separation index between the blank bead and the dim bead. And so for our membrane stain VF red, we've established a quality threshold of a separation index of at least 15. And for immunofluorescence, one can do a similar thing. So PE, which is probably the best, brightest immunofluorescent stain for immunofluorescence of EVs, we can set a threshold there. These fluorescence beads can be cross-calibrated against MESF standards so that we can report our brightnesses in those values. And what we can have here is just a little case study of one new instrument that a collaborator received. And when we ran the beads, we noticed that the alignment all looked pretty good. The separation on our membrane stain VF red channel was fine, but the performance on some of the other immunofluorescence channels on the other lasers was not up to snuff. And this let us flag this issue right away before we spent a bunch of time trying to measure vesicles. We had a service call, tuned up the instrument, and we're able to evaluate the improvement in performance across the channels and know that we have an instrument that's ready to go. And so that's an important first step in setting up an EV assay. I mentioned cross-calibration. That can be done by using some of the commercially available MESF standards to cross-calibrate rainbow beads in MESF units. And those would be suitable for use on your specific instrument that you perform the cross-calibration on. So now we'll turn to the vesicle size standard and its use in surface area calibration. So as I mentioned, we have a synthetic lipid vesicle we call Lipo 100. It's of a defined lipid composition that's similar to an average mammalian cell. It's been extruded through a nucleopore membrane so that it has a relatively uniform size distribution. Notably, it has lipids in it, but no proteins. We can take this liposome preparation and characterize it by orthogonal methods such as NTA and RPS. And then we can stain and measure those vesicles by flow cytometry. And the way we use that to estimate the size of our vesicles from their fluorescence is we take the fact that we know what the size distribution of the liposome is because we measured it by one of these orthogonal methods. If we know the diameter, we can calculate the surface area. And if we stain that liposome with VF red, we can measure its fluorescence distribution. So we have a range of vesicles here that range in size from somewhere less than 75 nanometers out to perhaps as high as 200 nanometers in this case. And if we perform a linear regression of these two distributions, the surface area distribution from NTA and the fluorescence distribution from VFC, we find a straight line. And the slope of this line can be interpreted as the number of fluorescence units per nanometer square of surface area. So we use this linear regression then to calculate the surface area of vesicles based on its fluorescence measurement, and then use geometry to calculate the diameter distribution. And so it's through this relationship between surface area and vesicle fluorescence that we derive our vesicle size estimate. And in practice, this is done via FCS Express's parameter math, where we can develop a calibration equation that will take the VF red fluorescence, use the slope and intercept from that linear regression to calculate an estimated surface area, and then use just geometry to calculate the diameter. And so that's part of the analysis layout for VFC that lets us present the vesicles in terms of their estimated diameter and go on and measure immunofluorescence. The size estimates by VFC are quite concordant with these orthogonal methods. So here's an example of some 293T EVs from culture media, which have either been unfiltered or filtered and measured by RPS or VFC. You can see the size distributions. You can see a dilution series to show that that size distribution doesn't really depend on the concentration. And if one looks closely, one can see slightly different size distributions based on whether these have been filtered or not through a 0.22 micron filter. So the size estimates are concordant with those other methods. And once you've done that, you can go through and do the rest of the essential controls, which include the dilution series I showed before, a detergent treatment to show that what you've detected really are vesicles. We can move on and start doing immunofluorescence using the appropriate positive and negative controls. A few words on light scatter. So light scatter is a very useful parameter. We use fluorescence to estimate size, as I mentioned, but we notice distinct differences in light scatter intensities amongst vesicles from different sources that are similar in size. And so, specifically in this example, we're measuring the light scatter intensity of our lipo-100 vesicles, as well as some platelet-derived and red cell-derived EVs. We find quite striking differences in light scatter, which is most likely due to the refractive index and cargo that those vesicles carry. So wrapping up here, we find that VF red fluorescence is proportional to membrane surface area, and that gives us a means to estimate vesicle size from fluorescence. We use the LiPo-100 standard, which has been characterized by orthogonal methods, and lets us determine the slope of fluorescent units per nanometer squared. VFC has the advantage that it's specific for membrane particles, including lipoproteins, which could either be a challenge or an opportunity. And finally, the diameter estimates we obtain are comparable with those other methods across vesicle types. So what are some of the limitations? Well, so we rely on those orthogonal methods to estimate our size distribution of vesicles. And those have their own limitations, which I'll refer to in a minute. We're estimating really surface area, membrane surface area. And so it's possible that if you have some specific EV types, and in our experience, viruses and virus-like particles are a couple of these, they have very high protein contents. They will tend to size a little bit small by this method because they are so loaded with protein. In those cases, one would simply use a preparation of virus or VLPs as the size standard. Lipoproteins are also detected, but as we, I think, heard earlier, These can often be distinguished by their distinctive light scatter. And finally, the instrument sensitivity does matter. If you can't detect the standard, it's going to be very difficult to detect, to estimate the size. A couple words on these orthogonal methods. Nanoparticle tracking analysis and resistive pulse spectroscopy are widely used. They're both useful tools in their context. They both provide label-free estimates of vesicle size, diameter in the case of NTA, volume in the case of RPS. But they're both non-specific. They'll detect any particle. They have their own limitations in terms of sensitivity and dynamic range. They don't really have a way to measure cargo by themselves. So they tend to work reasonably well in purified samples, but as sample complexity increases, they tend to be less useful. So just to summarize these various methods, they all have their strengths and weaknesses. NTA and RPS, in our experience, are useful for characterizing purified standard preparations, but less so for complex samples. Flow cytometry-based light scatter is useful, and the label-free estimation of size and refractive index are attractive, but they have the downsides of it's a pretty non-specific measurement, and the math is not simple, although it's made simpler by the software packages we just heard about. VFC has the advantage of being membrane specific, way to measure surface area, and it's formulated for high throughput analysis. Again, it depends on this external standard, which relies on those orthogonal methods, which have their own limitations. So to wrap up, counting and sizing individual nanoparticles is challenging. Counting and sizing EVs is even more challenging, but we've seen several approaches whereby flow cytometry can estimate EV size and refractive index, number and concentration, which is a subject on its own, as is the measurement of molecular cargo. Perhaps we'll touch on those in future tutorials. Common features of EV flow cytometry are a optimized calibrated instrument, appropriate standards, and appropriate protocols that are applied rigorously. Looking ahead, we can anticipate that there will be new flow cytometry instruments which will have improved sensitivity and resolution. We know that people are working on better and brighter dyes, and so both of these anticipated improvements are going to make our lives easier. And then finally, we can look forward to integrating the light scatter and fluorescence measurements I described here to develop EV refractive index as a useful parameter, which I think is going to be useful. So with that, I'll stop. Thank you for your time and look forward to your questions.